Okay, so we should now know that according to Newton's second law, the sum of all the forces that are acting on a system, or the total force, will cause the mass of that system to accelerate. And then you should also know that the sum of all the torques when it acts on a system will cause the moment of inertia of that system to accelerate. So that's what we know so far. Now the question is, what about if it was not accelerating? So if the system is not accelerating, then A is going to be equal to 0, and then 0 times anything is going to be 0. And then if it's not rotationally accelerating, then 0 times anything is going to be 0. So these are the two conditions for equilibrium. When the sum of the forces acting on a system is equal to 0, then it's not going to be accelerating up or down, and it's not going to be accelerating sideways. Whenever this is true, it's not going to be rotationally accelerating when you do that. So an example of this one was the painter, where you had a board, and then there was a rope pulling up with a certain force, and then there was another rope over here pulling up with a certain force, and then you had the weight of the person that was going down, and then you had the weight of the board that was going down. And so you could figure out, if you knew 3 of these forces, you could figure out the 4th one by remembering that if it's up, it's positive, and if it's down, it's negative. And then you would add all the forces, set it equal to 0, and then you could solve it for any of these 3 forces. So in the picture there that is on the right, we're going to do the same thing for a mobile that is rotating. So in this case here, you're going to have a weight over here on this side, and what's it going to do? So let's say that here's going to be my pivot point. So can you see that this weight would make it want to rotate in that direction? And then you got the fish. So the fish is over here, okay, and it is going to make the whole thing want to rotate in that direction. And then you got this weight on this side over here, and can you see that it's going to make it want to rotate in that direction? So we could calculate the magnitude of each of the torques, because we know that torque is equal to force multiplied by the radius. So we would know the weight of each of these objects, and we know the distance from the pivot point. So that's going to be the radiuses. And so we're going to sum them. But in the same way we said down is negative and up is positive, let's just say for the sake of argument that this is positive and then this is negative. So if it makes it want to rotate in this way, that would be a positive torque. If it makes it want to rotate this way, that would be a negative torque. It makes no difference. If you want to call this negative and this positive, it's perfectly okay to do that. And so we would sum the torques, set it equal to 0, and then we could solve it like for one of these 3 things the way you could solve this one over here for one of these things. Now, we're not going to do it. I just want you to know the concept of what does it mean for something to be in rotational equilibrium. So if it's in rotational equilibrium, it's not going to do this, and it's not going to do this. So it's going to stay put. It will not rotate if it's in rotational equilibrium. And that is like over here saying that this thing will not go up, it won't go down, it won't go sideways like this. So it's in equilibrium when that happens. Okay, just want you to understand, what do we mean by rotational equilibrium? You have to have rotational equilibrium when you're hanging a picture, otherwise the picture will rotate on you. And then you need to reposition the pivot point so that it hangs straight when you do that. So it's simple physics. Okay, let's take a break. When we come back, we will talk about what is rotational momentum.